Think about some of the heaviest things you can think of. What are they? A car, a tank, an elephant, a building? Now, for a second, think about how heavy you think a black hole is. NASA estimates that, on average, a black hole is about 6.6 billion solar masses. Solar mass meaning a sun. So it weighs basically 6.6 billion suns in our solar system. Now, obviously, when measurements get that big, when you're thinking astronomical scales, a lot of people tend to just either blank out or they can't picture how large that number is. So to put it in reference, if 1 kilogram is about 2.2 pounds, our sun, which we used to compare to the black hole being 6.6 billion suns, our sun is 2 times 10 to the 30th kilograms. That means 2 followed by 30 zeros kilograms. So it's about double that many pounds. To even further put this in reference, let's go back to the comparison I drew at the beginning of the video talking about African elephants. So each African elephant weighs about 5,000 kilograms. That would mean if you wanted enough African elephants to make up the mass of a black hole, you would need 4 followed by 26 zeros worth of elephants. 4 times 10 to the 26th elephants in order to make up the mass of a black hole. Now I'm going to put this number of, how many elephants there actually are to fit into the mass of a black hole. I'm going to put this number even further in a reference just to, easily grasp it. Estimates say there's about 10 to the 24 stars in the observable universe. So you would need more elephants than there are stars in the observable universe in order to make up the mass of a black hole. And I'm not talking a little bit more. We're talking about 2 orders of magnitude more. And a lot of people don't realize this, but adding 1 or 2 extra zeros to a number really does amplify it by that much more. It is that much bigger. One more final reference point that I'm going to place just to, solidify just how crazy the mass of a black hole really is how many seconds there's been since the Big Bang. The Big Bang happened 13.7 billion years ago. And since then, 4.32 times 10 to the 17th seconds have ticked by. So you would need more elephants than how many seconds have occurred since the Big Bang happened. Now that we've deciphered just how big the average black hole is, let's talk about some of the key components or pieces of a black hole. Probably the most well-known part to a black hole is what many people call the event horizon, or point of no return. Basically, when you get to the event horizon of a black hole, which is, it's not the singularity and it's not like the outside edge, it's just this perfect point where once you get there, you can't escape. And the thing about it is, a lot of people, kind of this misconception that maybe it's about how the pull is so strong that you just can't beat it. But the thing is, even if you were strong enough to beat the pull of the black hole, once you get to the point of no return, once you get to that event horizon, the space-time has bent around you in such a way that no matter which direction you go, you're heading to the center. And a lot of people find it really hard to visualize, but just think about if space-time and gravity and all that is just some flat piece of paper, consider the event horizon, the point where the black hole is just crumpled up that piece of paper, and once you get inside this ball of paper, no matter which way you go, every direction takes you right to the middle. It has bent space-time that much. And the main reason why it bends the space-time that much is due to just how insanely massive black holes really are. Moving more inward, the center of the black hole is a tiny, very, 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 very small point called the singularity. And basically what this is it's the point where gravity and all the mass and everything that the black hole is sucked in is so insanely strong and heavy and compact that it's collapsed on itself to a tiny, tiny, tiny point that you can't even, you wouldn't even be able to see it. It's so small. And the thing is, it's so heavy that it makes up most of the mass of the black hole. And it's just this tiny little point of singularity. And the reason they call it a black hole in the first place is because the gravity is so strong and so just insanely heavy that not even light can escape it. Even something traveling the speed of light, like light, couldn't even escape a black hole. It's that strong and that heavy that just light doesn't even escape. It's just darkness. And the thing is, a lot of people, when they look at the picture of the black hole that recently came out, they see the really dark part of the middle, the shadow of the black hole, which, it's a shadow because obviously light can't hit it and you can't see the black hole. but they also see what looks like just a spiral of light around it. And what that is basically when light and matter and energy gets super close to the black hole, gets sucked in, it's getting shredded, just eviscerated so strongly that it, it heats up and gets super, glowing red, and the energy and, charged particles, all that stuff are able to swirl around the black hole as they're getting sucked in. And the thing is, obviously, not everything's going to get sucked in at once, and some things just kind of spin around it in the black hole's gravity, and that is the glowing ring around it, which is just outside the point of no return, to where it's able to, in a sense, orbit the black hole, you could say. It's not necessarily orbiting it, but it's, just outside the point of no return, so it can kind of do some funky things like that. One of my favorite hypothetical pieces of information about a black hole is that if you're just outside the point of no return, or the event horizon, they would call it, where that glowing ring of, glowing energy is, if you were to sit there, the photons and just like light particles are moving so fast around that black hole that if you were to look forward, so if you're like, let's pretend you're sitting next to the black hole, you're like adjacent to it, and you're facing forward, or I guess you would say you're tangent to the black hole in that case, and you're facing forward, you looking forward, you would see the back of your head, because the light, by the time you look forward, has raced around the black hole and made it to the back of your head. So you would just be looking at and also the light from the back of your head would have traveled around also, so you'd be seeing the front and back of your head at the same time, which is really crazy to think about. Before we get any further into black holes, I think it's important to actually say what a black hole is. So for the most part, a lot of people love to say the fact that anything you could turn into a black hole, given enough pressure, given enough density, all that stuff. And the thing is, yes, that's true, but realistically, only certain stars can become black holes. And that's because, yeah, you could like squeeze a little tiny phone, and if you squeeze it hard enough into a small enough point, it would be dense enough to be considered a black hole. Because, if you had an infinitely tiny point with that much mass as a phone, it could be considered a black hole. But the thing is, what happens is, most of the time in space, when you have a big enough star, and there's like a lot of different equations that can explain like the size of the star needed to do it, but that's kind of just beside the point. Regardless, if you have a big enough star, and when the star dies and goes through its supernova and all that stuff, the mass of the star collapses in on itself when it grows to be like a red giant, stuff like that. And it gets so big and so heavy because, of all these different fusion and different reactions going on, that it collapses on itself, and then, space-time folds around it and it starts funneling in everything around it and just gets heavier and heavier and heavier, and that's how black holes start. Luckily, our star, our sun, is not big enough to become a black hole, which I'm saying luckily because, I don't know, I use that kind of loosely because obviously when our sun dies, we're going to die also, but I mean, at least it's not going to like suck us all into some crazy tiny singularity. Maybe it just might blow up in our face, which is a little better. Another fun fact about black holes is the fact that a lot of astronomers and cosmologists today, they theorize that at the center of every galaxy is a supermassive black hole. So obviously they haven't, seen every single one to prove it, but for the most part, the ones that we've seen so far, most galaxies, which galaxies are just groups of stars, planets, asteroids, comets, solar systems kind of orbiting together, a lot of the ones we've seen so far tend to orbit around a black hole. So at the heart of, for the most part that we know of, every galaxy, there is a supermassive black hole, which, supermassive is the distinction of, you got your little black holes, little, that we were just talking about, and then there's the supermassive, which are just beyond even comprehension how big they are. Anyways, ending this video, I'm going to talk about what would happen if you were to, cross the point of no return, and what would happen if you, an individual, were to get sucked into a black hole. One of my favorite theories of what would happen is, obviously other than your immediate death and possibly just blowing up and whatever, your matter spinning around and stuff, if you were, your body was able to hold together and be elastic enough, what would happen is, because the closer you get to the center of the black hole, the faster it sucks you in, just because of how, mass and gravity and all that works, if you were to go feet first into a black hole, let's just say you kind of just pencil dove into a black hole, what would happen is your feet would be getting sucked in infinitely faster at it, like an increasing acceleration to the top half of your body. So basically you'd be infinitely stretched, if you were super elastic, to the point of, they call it spaghettification, where you'd just be a giant, like atom thick noodle getting sucked into a black hole. And the way this works is because obviously, let's pretend you're like a 5'6" person, right? Just throwing out some random thing. You have 5 feet between the top of your head and the bottom of your toes, which doesn't seem like a lot, but in the sense of a black hole, which is, every centimeter you move up, it's that much faster. If you think about it, then the bottom half of your body is just going that much faster than the top half, to where you're just getting infinitely stretched. And that's kind of my favorite theory on what happens when you jump into a black hole. And a weird thing which plays into this when you actually do jump into the black hole is a lot of people theorize that, due to relativity and how, you experience things differently relative to how fast you're going. If you were to be getting sucked into a black hole, let's say at about the speed of light, obviously it's impossible to go the speed of light, but due to the fact that black holes can suck in light, a lot of people think, you could be getting sucked in faster than the speed of light. That's for another video. But anyways, let's pretend you were getting sucked in at the speed of light. The faster you move relative to light, the slower you experience time. So to an observer seeing you on the outside, right, they see what appears like you're getting sucked in forever, right? They're looking at you from the outside of the black hole. They're past the event horizon. Let's just pretend there's an observer watching you get sucked in. They could watch you for their entire lifetime. They could watch you for the entire lifetime of the universe, for the most part. And to them, you're just slowly, ever so slowly getting sucked in. But to you, the person going the speed of light, you just see the entire everything happen in one snap, and then it's gone, because you're moving at the speed of light, so it's just boom, gone. But the person watching you on the outside, because of the way relativity works, they just see just slow motion, you getting sucked into the black hole. Anyways, it's been Bold Assumptions, Black Hole Facts. I'll see you guys next time.